Here we're looking at three different limits as x approaches infinity of different rational functions. So for this first rational function, if I imagine plugging in infinity everywhere I see x, the infinity to the fourth power and this infinity to the fourth power, those are the highest degrees. So that means those terms are the only ones that are truly having an impact overall as I approach infinity. So when I have this situation where the degree of the numerator is equal to the degree of the denominator, these two terms are the only two that I have to focus on. So I'm going to rethink of this as negative 18 x to the fourth over negative 42 x to the fourth. Now these two, the variables here have the same degree, so they really are just canceling each other out. So I just need to focus on these leading coefficients. A negative divided by a negative will create a positive, and 18 over 42 can be simplified. They have a common factor of 6. So this would simplify to 3 over 7. So in this instance where we have the same degree in the numerator and the denominator, we're actually just dividing the leading coefficients of those terms. Be careful not to lose any negative signs. In this second example, we're also approaching infinity, but here when I look at the degree of the numerator, I see that is greater than the degree of the denominator. So let's think about what would happen if I actually plugged in the idea of infinity here. So I would have 3 times infinity to the fifth plus 1 over 2 times infinity to the third. Now I can't actually just plug in infinity because it's a concept of a number, it's not an exact value, but we're just going to try and think through this. So if I have a really big number to the fifth power, that is going to be much larger than a really big number only to the third power. So in that case, this numerator ultimately wins out over the denominator, and this would be equal to just infinity. We know for limits that anytime a limit, when we evaluate it, is equal to infinity or negative infinity, we can simply express that as does not exist, or D&E. And this occurs the fact that we have a limit that does not exist because there's actually no horizontal asymptote for this type of rational function where the numerator has a greater degree than the denominator. Okay, and for our last example, here we have a numerator with a smaller degree than the denominator. So in this case, again, let's think about plugging in infinity, even though that's not technically something we can really do, we can just think through what that would mean. So here we would have, in the numerator, infinity to the second power, but that's not nearly as big of an impact as this infinity to the third power in the denominator. So this infinity here is really taking over the expression as a whole, which means this is really going to some number over infinity. So this denominator is going to be much larger than what is in the numerator. Anytime that I have some number divided by a giant number, that really is just approaching or moving toward 0. So that is why in this type of rational function, where we have a smaller degree in the numerator and a bigger degree in the denominator, there's a horizontal asymptote of 0. So this limit is just equal to 0.